In this video, we're going to calculate the de Broglie wavelength of a proton that weighs 1.67 times 10 to the minus 24 grams and has a velocity of 2.11 times 10 to the 6 meters per second. So we're going to use our de Broglie wavelength equation. So that looks something like this. So the de Broglie wavelength looks like this. So it's going to be our lambda, which is in meters, or our wavelength in meters, is equal to Planck's constant h, its units is joules times seconds, divided by our mass, which needs to be in kilograms. That's going to be multiplied by our velocity, which is in meters per second. So looking at the values we've been given, we have 1.67 times 10 to the minus 424 grams, and we have a velocity of 2.11 times 10 to the 6 meters per second. Our velocity is already in the correct units at meters per second. Our weight, though, needs to be converted from grams into kilograms. So let's do that first. So we're going to take our 1.67 times 10 to the minus 24 grams. We know that for every 1 kilogram, it's going to be 1,000 grams. So this is going to turn into 1.67 times 10 to the minus 27 kilograms. So very, very, very small mass. Now that we have everything in the correct units, we can now plug this into our equation. So our lambda, our wavelength, is going to be right there. We're going to take our Planck's constant, which is 6.626 times 10 to the minus 34 joules times seconds. That's going to be divided by our weight in kilograms, which is 1.67 times 10 to the minus 27 kg. And that will be multiplied by our velocity, which is 2.11 times 10 to the 6 meters per second. All right, so let's go through and let's solve for this. So we have our joules per times seconds on top, our kilograms on bottom, and our meters over seconds on the bottom. So let's just get to our number first, and then we'll worry about our units. So if we plug this into our calculator, our lambda is going to come out to 1.88 times 10 to minus 13 meters, or 1.88 times 10 to the minus 4 nanometers. Now let's show how we got there using those units. So I'm going to get rid of our numbers and just leave our units here on the page. So we know that our lambda should end up in meters. So somehow meters is going to equal to joules times seconds over kilograms times meters divided by seconds. So if we rearrange this, get rid of all of our fractions within a fraction, especially this per second on the bottom, what this is going to look like is joules times seconds divided by kilograms times meters. All we did was we took our seconds here on the bottom, we moved it up to get it out of a fraction within a fraction. Now, something interesting about this is that joules times seconds, or joules times seconds squared, put that over here on the side, joules times seconds, which is equals to joules times seconds squared. That unit as a whole is also equal to meters squared times kilogram. So if we take this meters squared times kilogram, and we plug that into the top, things are going to make a little bit more sense of how we end up with this final unit, which is just meters. So this is now going to look like meters squared times kilogram divided by kilogram times meter. Now if we go through, we know that our kilograms will cancel out because one is on top and one is on bottom. We have meters squared on top and meters on bottom, so the meter on bottom disappear, that squared disappears, and that will ultimately leave us just with our meters for our final answer. So it is very important that we go through and we solve for our units just as much as we solve for our number. So we don't make any mistakes in our math, we make sure that everything lands in the correct spot.